Hello students, a function f from a to b, a non-empty set a to non-empty set b is said to be 1, 1. If every member in the domain have different images, they must have different images. Every member of the domain have different images. It is that simple actually. Okay, the definition is that simple. The 1, 1 function definition is that simple. Now, where is the problem when we are going to discuss when both domain and codomain are finite? It is can be very easily seen whether a function is 1, 1 or not, simply by seeing the fact whether the images of every member in the domain are different or not. But when these two sets, domain and codomain, are infinite, like n, like r, like z, and the function is not that simple, then it becomes little bit difficult to check whether a function is 1, 1 or not. Not difficult, but it becomes little bit hazy than this. Okay, so we are going to discuss different ways of showing a function to be 1, 1. So basically this concept is this only. Okay, so only difference will be this, sets will be different, and probably most of the time they will be infinite sets. Now before we move ahead, in order to prove, in many questions we have to prove whether the function is 1, 1. If it is 1, 1, we have to prove it. Okay, so let us discuss how to prove it, how that concept of proving will come, because in order to prove, we have to show that every member in the codomain are the different images of the member of the elements in the domain. Okay, so let us derive one technique from here. 1-1ness doesn't mean that whenever this images are equal, suppose I have taken one more C here, so I must get, if I get another C repeated in the set of B, so I must get the pre-image of that C also to be 3. 3 has only one image, means if I consider two equal images in the codomain, I must get the same pre-image for the two equal images. Okay, the other way around we can say like this, when the same thing can be said like this, when two images are different, C is not equal to D, then their pre-images are also has to be different. That also going to prove that a function is 1, 1. So we are going to derive it. So whenever we have to prove a function from a non-empty infinite set, suppose R to R, and if we have to prove that this function is 1, 1, so what we'll do basically, we'll consider fx1 to be equal to fx2 for x1, x2 belonging to the domain, which are the domainer. And by using the definition of the function, we are going to show that if we can show that x1 equal to x2, only x1 equal to x2 only, if the functional definition will imply x1 is equal to x2 only, we must get only this result, no other result ever associated with this, then we'll be able to say that this function is 1, 1. On the other hand, if we can show that same way, means either this, or if we take this one to be not equal, fx1 is not equal to fx2, and if we can show that x1 is not equal to x2 only, then also it will prove that the function is 1, 1. Okay, so most of the time we are going to do this, and there is another way of doing this, whether a function is 1, 1 or not. So basically in this class we are going to discuss all of them. Okay, so basic meaning of 1, 1 function is this. Okay, so let us take a few examples. Okay, let me take one example. Suppose f from R to R, real number to real number, and fx is given by x squared plus 1. And we have to check whether this function is 1, 1 or not. Okay, so there are many methods actually to prove this function to be 1, 1 or not 1, 1 actually. So let us go for the first one what we have discussed just now. So let x1, x2 are two members in the domain such that fx1 is equal to fx2. You can go for fx1 is not equal to fx2 also. Okay, so fx1, the functional definition says x1 square plus 1 equal to x2 square plus 1. So ultimately we'll get x1 square minus x2 square will be equal to 0. So we'll get x1 plus x2 into x1 minus x2 equal to 0. So we'll be getting either x1 equal to x2 or x1 equal to minus x2. Now that time we just now I had told. So whenever we are applying this, we have to make sure that we will get only x1 equal to x2. And if we are getting anything else along with this, we have to make sure that this result doesn't stand. But in this case, x1, x2 are real numbers, so x1 can be equal to minus x2 also. So this x1 plus x2 for some real number can be equal to 0. Okay, x1 plus x2 for two real numbers can be equal to 0. So both these results are possible in this case. So we are not looking for two results, we are looking for only one result. So we can clearly say that f is not 1. Okay, so this is first method. First method, it can be done either this way, we have proved that it is not 1, 1. Again, for disproving, for saying something to be not true, we can always give example. They are called counter example. Okay, so one counter example also can be given here. This is the same method actually. Either we'll prove it to be not 1, 1 or we can give counter example. Counter example will be, suppose I will take f of 1. F of 1 will be 2 and f of minus 1 also will be equal to 2. Showing us that 1 and minus 1 have the same image 2. This 2 is associated, 2 in the codomain is associated with two different members in the domain, showing us that this function is not 1, 1. So in this method we can do two ways. If it is no, either we can prove it to be no or we can resort to the counter example. Again, this is the method 1. This is first method, method 1. For proving or disproving a function to be 1, 1. Okay. Now let us go for the second method. And this second method is a very, very useful method. This is the graphical method. Okay. So let us go for, let us take the same question for the second method, method 2. So what we do in the second method, we will try to draw the graph of the function. Okay, it is a quadratic function. The basic function is fx equal to x square, and we know that how to get the, we know x square equal to, x square is a parabola passing through origin. Okay, x square plus 1 obviously will be a parabola passing through 1, 0. Right? So this will be the graph of y equal to x square plus 1. Now we have to learn how to analyze one-oneness from the graph of a function. Again, so let me bring that one-one definition again here. Here are the values of x, and here are the values of fx. That we say y. Right? So a function will be 1, 1 if for different values of x we'll get different values of y, that is fx. Now here we have seen that if I consider one line parallel to x-axis, any line which is parallel to x-axis, this is one of the lines. Okay, this line is intersecting the graph at just two different points, and if I draw two perpendiculars, I will get two values of x, say x1 and x2, of which the functional value fx1 and fx2 are same, because these ordinates are same, right? These ordinates are same, so we are getting two values of x1, which are not equal. This x1 and x2 are not equal, but we are getting the same fx value, so saying us that this function is not 1, 1. So basically, graphical method, how to check whether a function is 1, 1 or not. What we'll do, after drawing the graph, of course, we'll draw some line which are parallel to x-axis, and if one of those lines cut the graph of the function at more than one point, just like here, just intersecting at 2 points, more than 1 point, then we'll conclude that the function is not 1, 1, because of this x1 and x2 will have the same functional value. fx1 and fx2 are same. fx1, this is fx1, and this is fx2. This and the same ordinate are same. Okay, so this is the second method, and this method is quite useful. Okay, this is a very, very useful method, and we must learn how to draw the graph of different simple functions. Okay, this is the second method, method 2. So we'll discuss another method actually. Okay, let us go for the third method before we move to the next question. The third method, there are many methods again. The third method, what we'll do, we'll try to use differentiation. Okay, so we'll find out f dash x, which will be in this case 2x. Okay, what we'll look for here in the differentiation method, whatever the function is, its derivative in its domain must give me either positive values or negative values. Okay, f dash x for the values of x, that is in the domain, must give me either positive values or negative values, not both. Not both in the sense, suppose this here in this example, 2x will be positive whenever x is positive or 0, and negative when x is negative. So the domain part, this domain part, for some portion of the domain f dash x is positive and some portion of the domain f dash x is negative. So I cannot decide whether f dash x is either positive, entirely positive, or entirely negative. In some portion of its domain it is positive, in some portion of the domain it is negative. So in this case we'll conclude that the function is not 1, 1. F is not 1, 1. So when we'll say by this method whether a function is 1, 1, we must be able to conclude f dash x sign exclusively whether it is positive or negative, exclusively. Okay, either it has to be positive or negative in the entire domain of the function. Then only we'll be able to say that function to be 1, 1. And in this kind of cases, some part of the domain it is positive, the other part of the domain f dash x is negative. In this kind of cases, we'll conclude that f is not 1, 1. Okay, so this is the third method. So we can use any one of these three methods to check whether a function is 1, 1 or not. Okay, let us discuss a few problems. Okay, fx equal to x squared plus 1. This question again can be twisted. Let me check. Not twisted, it can be changed. Suppose let's start with w. W means the set of whole numbers. Whole number to r. Now is this function 1, 1? Whether this function is still 1, 1 or not. We have changed the domain to w. So I'll try to do by all the three methods here. Okay, method 1 here, method 2 and method 3. So method 1, what will do? Let x1, x2 belongs to our domain is W now, such that fx1 equal to fx2. So ultimately we'll be getting x1 square plus 1 equal to x2 square plus 1. So ultimately we'll get x1 equal to x2 or x1 equal to minus x2. Now the thing is that x1 and x2 are whole numbers. So two whole numbers, we cannot get two whole numbers whose sum is 0, right? This one is nothing but x1 plus x2 equal to 0. We cannot get two different whole numbers whose sum is 0. Again, x1 x2 are two different numbers. So this result is invalid. So we are living with only x1 equal to x2 whenever we are assuming fx1 to be equal to fx2, because we are taking x1 and x2 are two different whole numbers in two different whole numbers, right? So here we'll declare that f is 1 now. So it all depends on the domain actually. Okay, so this is the first method. And the second method, we'll try to draw the graph. So here domain is only whole numbers, so we don't record the negative part. X square plus 1, so the same graph will come actually. The negative part will not be there. So the graph will be only this, will start from 1. So again, if I'll draw some line parallel to x-axis, they are not going to cut this graph in more than 1 point. Obvious reason, because this part of the graph is not present now. Okay, so showing us that this function is 1, 1. Okay, the third method, f dash x equal to 2x. Is it not will be greater than equal to 0 for all x? Because x are now whole numbers. Okay, so f dash x equal to 2x. So we can exclusively find out the sign of f dash x. Okay, for the entire domain, that is whole number, that f dash x is positive. So clearly showing us that function is f is 1, 1. Here also this implies f is 1, 1. Okay, so these are the three methods we need to know to start with, at least whether a function is 1, 1 or not. Okay, so let us go for the next question. Okay, let me take next question. Fx equal to 3x plus 2. F from R to R is 2 is the question to be discussed actually. Okay, so fx equal to 3x plus 2 R to R. So again we can, is it not very easy? So we'll take simply, let me take again three methods. All the three methods. Let x1 x2 belongs to R, which are both are R. So we'll write domain R such that fx1 is equal to fx2. Okay, so fx1 will be equal to 3x1 plus 2, 3x2 plus 2. So simple calculation will give me x1 equal to x2. So f is 1, 1. Okay, the second method we are going to draw the graph of it. Fx equal to 3x plus 2. So we'll take this one as y equal to 3x plus 2. So y equal to 0, x equal to minus 2 by 3, and x equal to 0, y equal to 2. X equal to 0, y equal to 2. Something I have done wrong. If x equal to 0, y equal to 2, and if y equal to 0, x equal to minus 2 by 3. Y equal to minus 2, something like this. So slope is positive. Again, so this one is y equal to 3x plus 2. Y-axis, x-axis, horizon. Okay, so what we have to check whether any line parallel to x-axis cut this graph in more than one point. There is no chance that any one of these horizontal lines which are parallel to x-axis will cut the line, the graph. This is the graph line y equal to 3x plus 2 will cut at more than one point. So we imply that f is 1, 1. The third method, what we'll do, we'll find out f dash x. So what we'll get f dash x equal to 3 is in the exclusively positive. F dash x is 3, which is greater than 0 for all x belonging to R. What is R here? The domain of the function. So we can exclusively say that this f dash x is positive. So immediately we'll imply that f is 1. Again, let us go for the next question. I hope it is clearly understood. Okay, just change the definition of the function and domain and range. Let me quickly take a few more questions. Fx equal to x cube plus 3. Okay, f from R to R. Fx equal to x cube plus 3. Okay, we have to check whether it is 1, 1 or not. Again, I have to go for all the three methods. Method 1, method 2 and method 3. Method 1, we'll consider x1, x2 to be in the domain. Again, domain, codomain both are R, so we'll specify which R we are talking about, the domain R, such that fx1 is equal to fx2. So simply we'll get x1 cube plus 3 is equal to x2 cube plus 3. Simply x1 equal to x2 here. Okay, so we'll be getting only one what is it called? Result is coming out of this. So we'll declare that f is 1, 1. Okay. There's a second method, graphical method. So we have to draw fx equal to x cube plus 3. So x cube plus 3 will be passing through origin plus 3, so it will pass through the point 3, 0, 0, 3, sorry. So y equal to x cube plus 3 will be something like this. Again, so what we have to check whether any line which is parallel to x-axis cutting this graph in more than one point. No chance, right? There is no chance that any one of these lines is going to intersect this graph in more than one point. So immediately implies f is 1, 1. In the third method, we'll find out f dash x. What we are going to get 3x square. Now then, 3x square and what are x? X are real numbers. Can we make out something here? Now, x square is not always will be positive or 0 for all real numbers. So we can say that this value, this particular value will be always greater than or equal to 0 for all x belonging to the domain that is R. So again, we are exclusively saying that f dash x is positive here. So immediately imply that f is 1, 1. Why we need to know all the three methods? Because we never know which question will be easier by which method. And some of the questions they are very easy by this method. Some of the questions they are very easy by this method. Some of the questions they are very easy by this method. So we need to know all the three methods equally well actually. Okay, we'll go for the next question. Okay, for the next question is fx equal to x square plus x, x square plus x, and f is running from z to z. Z is a set of integers, so it is running from integers to integer, and the function is defined as fx equal to x square plus x, quadratic function. Okay, so whenever we get quadratic function like this, we'll try to simplify it to method of computing square. Okay, so if I'll use the what I'll get x plus 1 by 2 whole square minus 1 by 4, right? Yes. Okay, so again we'll go for all the three methods. Method 1, method 2, method 3. Method 1, method 2, method 3. Okay. So what will method 1 what we do? Let x1, x2 belonging to the domain. Domain is z, both are z, so we'll specify which z we are talking about, that is domain, such that fx1 is equal to fx2. So what we'll be getting x, you can write any one of these two, so I'm going to write this x1 plus half whole square minus 1 by 4 is equal to x2 plus half whole square minus 1 by 4. Minus 1 by 4 cancels each other. So if I'll take square root, I'll be getting x1 plus half is equal to plus minus x2 plus half. So I'll be getting x1 plus half equal to x2 plus half. So I'll get x1 equal to x2 or I'll be getting x1 plus half is equal to minus x2 minus half. So I'll be getting x1 plus x2 plus 1 equal to 0. I want to check whether both these results are possible in this domain or not. So x1, x2 are integers here. So two integers which are equal are possible. Obviously, this one will be possible. I have to check whether this one is possible. Two integers, their sum is equal to minus 1. Is it possible? Yes. There are many integers whose sum is equal to minus 1. Or there are two integers x1 and x2 whose sum, when it is added with 1, we get 0. Same thing. So both these cases are possible, and that is what we are not looking for a function to be 1, 1, right? So the conclusion is f is not 1, 1. Okay. So whenever we get multiple results, we have to check whether both are true or not. If any one of them, not any one of them, this one is required, only this one is required. If the adjacent cases with x1 equal to x2 can be discarded, and we are living with only x1 equal to x2, then only we are then we are going to conclude that it is going to be 1, 1, otherwise no. Okay. The second method, the graphical method, obviously. Quadratic, we know that it is going to be a parabola. All we have to find out is vertex. Its vertex. Okay. How to get the vertex? Vertex of ax square plus bx plus, vertex of ax square plus bx plus c. What is it? Minus b by 2m and minus d by 4m. These are the coordinates of the vertices. So getting the coordinate of the vertices are very, very important to draw the graph of a quadratic polynomial, especially quadratic function. And we have to check what is the coefficient of the highest power. Highest power coefficient is 1, positive, so it will be concave up. Okay. and the vertex of the parabola will be minus b by 2a and minus d by 4a. Now let us check what is that. Minus b by 2a is here, minus b, a is 1 here, a is 1, b is 1, c is 0, there is no c here. Okay, so minus b by 2a minus 1 by 2 and minus d. D is what? That is the discriminant. D equal to discriminant, it is b square minus 4ac. So b square is 1 minus 4ac equal to 0. So minus 1 by 4. So this is the vertex. Minus 1 by 2 minus 1 by 4. Minus 1 by 2 minus 1 by 4, somewhere in here. Okay, so the parabola will it pass through origin when x equal to 0, y equal to 0, right? When x equal to 0, y equal to 0, so it will pass through origin. So the parabola will be like this. Okay, and the vertex is, we have found out the vertex to be minus 1 by 2, minus 1 by 4. So we have roughly draw the graph of the function fx equal to x square plus x. Now we have to conclude whether this function is 1, 1 or not. So obviously there are infinitely many instances. For example, x-axis itself, it has got 2 points, these 2 points. But the values of x are different, but the values of fx are same, 0, right? So there are infinitely many instances we are going to get, lines we are going to get which are parallel to x-axis, cutting the graph in more than 1 point. So showing us that this function is not 1, 1. Okay, let us go for the third method also. Let us discuss that also. Method 3. So what we do in the third method, we find out the derivative of the function, given function. So let us do it. F plus x will be equal to 2x plus 1. Okay. Now we have to check whether it is positive or negative. We need either positive or negative exclusively. Okay. What are the values of x possible here? X is here, z. Now this value, the value of 2x plus 1, is positive when x is greater than or equal to 1. X is greater than or equal to minus half, really. Any integer which is greater than or equal to minus half, we are going to get this one to be equal to positive, and negative if x will be lesser than minus half. For any integer which is less than minus half, we are going to get a negative value, and for any x, any integer which is greater than or equal to, there is no integer equal to minus half, sorry, greater than minus half, this one will become positive. So we are not getting any exclusive sign here for f this x. Okay, in some portion of x it is positive, the other portion it is negative. Okay, that is not what we are looking for. Okay, so therefore the function fx is not 1, 1. Okay, so this 3 methods, again we have done this question by 3 methods. So next coming up questions, we are going to discuss whatever method will be suitable for that particular question. Okay, let's go for the next question. Okay, this one is f is running from 2 to infinity. 1 to infinity. Domain is 2 to infinity and codomain is 1 to infinity, closed interval. And fx is given by x square minus 4x plus 5. Again, and we have to check whether this function is 1, 1 or not. Okay. Okay, quadratic become x minus 2 whole square plus 1, right? So second method will be easier here. So let us draw the graph of it. X minus 2 whole square plus 1. X square, then x minus 2 whole square, x minus 2 whole square will be shifted 2 units here, then plus 1 will be shifted 1 unit here. So it will be a parabola passing through this vertex will be this point. This point is x equal to 2, y equal to 1. So basically the graph of this function will be this point is 2, we can find out the what is it called, vertex, by using that minus b by 2a minus d by 4a. We get the same thing. Okay, so this is the graph of y equal to x square minus 4x plus 5. So what we are looking for, 1, 1 is, so there are definitely more than one instances where we'll get some lines which are parallel to x-axis cutting the graph at more than one point, showing us that the function is not 1. Okay, let me take another question. Okay, let me take this fx. Let me take this lesson f from R to R, given by fx equal to 2x cube minus 6x squared minus 18x plus 17. Okay, fx equal to 2x cube minus 6x square minus 18x plus 17. It is running from real number to real number. We have to check whether this function is 1, 1 or not. Okay, so cubic function, we'll go for the third method. Okay, and let us find out the derivative method f this x. So what we get here f this x equal to 6x square minus 12x minus 18. 6 can be taken common, so we'll be living with x square minus 2x minus 3. Let me factorize it. X square plus x minus 3x minus 2x minus 3. Okay. Now what we have to do after finding out f this x, we have to check for what part of x. Means we have to check whether this value will be positive or not, right? Positive or negative or not. Okay, we are looking for either positive or negative exclusively for all the values of x in the domain, right? So let me check. We know how to check, how to get whether this value is, where it is positive, where it is negative, right? We know the wavy curve method. So let us get that. So critical points are minus 1 and 3. Both x are positive, so it will start with positive, negative, positive. So this diagram is depicting whether this particular value is positive and where it is negative. So f dash x is positive for all x lesser than minus 1, lesser than equal to minus 1, or x is greater than equal to 3, and is negative for all x lying between minus 1 and 3. Right? So f dash x have not all we have to check whether these values of x are possible or not. Okay, what are x? X is a real number, so all these values are possible. So what we have got, the sign of f dash x is positive in some part of the domain, and the sign of f dash x is negative in some other part of the same domain. Okay, that is not what we are looking for to be able to say, to be able to call a function to be 1, 1. So we will conclude f is not 1, 1. Okay, let me go for one last question. Okay, maybe two more questions. Okay, let's go for it. So one question in the NCERT will take. Many students, they used to ask me this question. It's really very easy question. F from n to n. Fn equal to n by 2 when n is even, and n plus 1 by 2 when n is odd. What is n to n? Is natural number to natural number. We have to check whether this function is bisective, but we are going for 1, 1 now. Okay. Now clearly, this function, clearly it is not 1, 1. Because we have a very strong counter example here. In fact, many counter examples. F of 2, let us find out f of 2. 2 is even, so we'll go for this functional definition. So 2 by 2, 1. And let us find out f3. So what we'll get? f3. 3 is odd, we'll go for this. So 3 plus 1 by 2, okay. I should have gone for 1. Okay. Let us go for 1. 1 is still odd. So it should have been 1 plus 1 by 2, that is 1. So f1 is also 1 and the same as f of 2. So in the domain of natural number, and codomain is also natural number, what we have got, 1 and 2 have the same image 1. So the function is not 1, 1. Okay. Let me go for the last question. F from R to R given by fx equal to x into power x. Okay, this function we have to check whether it is 1, 1 or not. Okay. The first method, for doing this question by first method, this will be very, very difficult task. Okay. In fact, we will not be able to conclude anything by first method. Second method, drawing the graph. Yes, we can draw the graph of it. We will go for the third method. Okay, third method, that is f dash x differentiation method. That will be the easiest for this function f dash x. How to get? How do I know? Okay, it comes out of practice. Okay, so which function has to be dealt with which method? Okay, so f dash x will find out. What we get? X e to the power x plus e to the power x. So we get x e to the power x is common, and we get x plus 1. Now we have to check whether this particular value is positive or negative exclusively in its domain. Again, we know that e to the power x is always positive. So whether f dash x is positive or negative, it will depend upon where x plus 1 is positive or negative. Right? So obviously, quite clearly we can say that this value will be positive. Which value? This f dash x, it's this entire value. Whenever x is positive when x is greater than or equal to minus 1. And this particular value will be negative when x will be lesser than minus 1. Okay? Now all we have to check whether these values are possible for the domain of the function or not. What is the domain of the function? R. Is it possible? Yes, both these intervals are the part of the domain. So in one part of the domain, the f dash x is positive, the other part of the domain the negative. So we'll conclude the function f is not. Okay, so this is the way to solve for 1-1 function. I hope you have understood. We'll take some more questions when we'll go for onto functions. The coming up class will be on onto function. Then we'll club 1-1 and onto, and we'll discuss about the bijective function, that is invertible functions. Okay. Till then, thank you. Thanks for watching.